Okay, up until this point, we have studied asymptotes and we've looked at rational functions, and we've been able to determine if something was a whole or if it was an asymptote, which created infinite type of discontinuity. So we've seen removable and infinite discontinuity. Today we're going to look at items that would cause a jump in an equation. Okay? So a piecewise function is made up of separate parts. Okay? And those separate parts are known as sub-functions. They are sub-functions. Oops, sorry, I clicked on the wrong part. They are sub-functions. Different equation, each portion is defined by a different equation over a different interval or a subdomain. So they have the overall domain and we have subdomains. So here I have two subfunctions, and this is the subdomain. I'm going to use this top function for every value where x is less than -2, and I'm going to use this function whenever x is greater than or equal to -2. So let's go back to a basic skill that hopefully you learned before. An open circle represents, an open circle represents not included. Not included. The value is not included. So for example, right here, -2 is not included. Okay? So we would use less than or greater than. Those are not included. If I have a closed circle, what happens? It's included. Included. It is equal to. So that would be greater than or equal to, less than or equal to. I went in reverse that time, sorry. Everyone good? Okay, the functions that we're going to focus on are basic ones that you would have graphed or learned how to graph in Algebra 1, so linear functions and quadratic functions. Yes. Subdomain is the domain specific for that piece of the function. So we've been studying the overall function of the entire graph because most of the graphs that we've been looking at either have a hole or they have, they have removable discontinuity or they have infinite discontinuity. So we've been doing the union set, and now we're going to focus on separate domains for separate pieces of a function. So you have one graph that has different functions, so they're called subfunctions, different pieces, and each of those has a separate restriction. No. And why is there not? Well, it's not continuous. Okay? All right. Each one of these, if you notice right here, that's a jump. Okay? And there was some still confusion about removable and jump. If you have a graph that comes together like this is not a jump. This is removable, and this is a point that can fill that removable. It is not a jump because both sides of the function come together. And that is going to be very, very important when we talk about limits. So if you notice, there's two graphs, right? There's two separate points, and those points don't overlap. Here they touch. The two sides of the graph touch at this point, and this is just a point to kind of fill in that removable spot. Okay, so this is removable because both sides of the graph meet at that removable spot. Here I have a removable, well, it's not removable. Here I have a hole, but the two sides of the function don't meet together. It's a jump. When they don't meet, it's a jump. Okay. All right, so we have three subfunctions here. The first one is -x minus 3. What type of function is that? Linear. Good job. The second function is x squared plus 1. What type is that? Quadratic. And the last one is 3, which is that, yes, it is linear. Y equals 3, okay? We're going to note that this is less than -3. This is greater than or equal to 3, less than or equal to 2, and this one is greater than 2. Okay, those are our subdomains. Okay, sorry. So, what numbers, if I'm looking at numbers less than 3, what's my domain going to be from where to where? Negative infinity. So the first one here, its domain is negative infinity to negative 3. Is it going to be a curved or square bracket? Which one's it going to be? X less than, what is it going to be? It's going to be curved because it does not include negative 3. Okay? Now this one, what's my domain? From where to where? It's going to include negative 3, and it's going to go to positive 2. Yes. And the last one is going to be from where to where? This one, what's the domain? 2 to what? Infinity. Okay? So those are my 3 separate domains. Okay, so now we're going to plot each of these graphs. To me, the easiest way is to use the values that they've given, pick a couple points, and plot it. Okay, and I'm going to do it in different colors. So this one, we can use anything smaller than negative 3. Negative 3 is the last value I'm going to use. So I'll make a quick little table of values. Negative 3, can you give me 2 other values that you would like to use? Negative 5, and I heard something over here. Negative 6. Great. I'm simply going to plug it in. Negative 1 times negative 6 minus 3. 3. Negative 1 times negative 5 minus 3. What does this say? Anything smaller than negative 3. So I'm going to use negative 3, and I'll show you why in a second. And then I chose some other numbers. You can choose any numbers you want as long as they're smaller than negative 3. Okay, so negative 1 times negative 3 minus 3 is 0. Okay, this one is very important. What type of dot am I going to put for negative 3, 0? Open circle. Negative 3, 0, open circle. Negative 5, 2. And negative 6, 3. So my function goes like that. Everyone clear on that? Okay, now I'm going to look at this quadratic. And I'm going to go, negative 3 is going to be my starting point. And my final point is going to be 2. And I got that because my start and my end were given to me. Whatever this start and this end is, that's definitely going to go in my table of values. Let's pick 2 numbers between negative 3 and 2. I'll pick an easy one for you, 0. Negative 2. I like the negative 2. All right, what's negative 3 squared? Right, but it is a reference point, so I had to include it, and I put an open circle there because it does not include that value. But this has to be part because that is a reference. Yes. And we just do an open circle. All right, negative 3 squared plus 1, 10. Negative 2 squared plus 1. 0 squared plus 1. 2 squared plus 1. 5. Okay, so at negative 3, I'm going to go up to 10. Does yours have 10 lines? All the way to the tippy top? Okay, so let me raise the screen so I can be there with you. Okay, the tippy top is 10. Let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You are absolutely correct. Open or close circle. Thank you. And then I'm going to go to negative 2, 5. 1, 2, 3, 4, 5. I'm going to go to 0, 1. And I'm going to go to 2, 5. Boom. Why did I put a solid dot at 2, 5? Why did I put a solid dot at 2, 5? Because it's included. It's less than or equal to. Make my little curve because I know it's quadratic. Done. That graph is done. Okay, so this graph confuses a lot of students. Who can explain that to me? Y equals 3. What's that going to look like? What's my output going to be? I'm seeing a lot of straight lines. Yep, I see a lot of people showing me a horizontal line. Okay, so I'm going to pick 2 and give me 2 numbers bigger than 2. 4 and 5. And each time, what's my output going to be? 3. Every time, it's going to be 3. So I'm going to find 2, and I'm going to go up to 3, and is it going to be open or closed? Open, and I'm just going to make a horizontal line. Done. So that is our finished product. Well, that is a linear function. That's okay. A linear function can be a single number. If it was x equals 3, then it would not be a function because it would fail the vertical line test. Okay? Are we good? All right, let's go ahead and flip our paper over. Yes. Why at 2, 3 is it whole? Because when I look at the information, it's greater than, not greater than or equal to. It has to be equal to for me to fill in the circle. Good? Good question. All right. Let's move on to the next one. Okay, so sorry, I forgot about this cubic one, but it doesn't matter because it's the same process. For each one of these, you're going to make a table of values. You must include, even if the number isn't equal to, you must include the reference numbers that they gave you. Okay? And you're either going to put a closed circle or an open circle. So this number is important, this number and this number is important, this number is important. You're going to make a table of value. If you're lucky enough and you carry colored pens or colored pencils, sometimes for this concept, I should have told you, it's nice to do each function in a different color until you get used to it. It's not necessary, but some people visually, they like it that way. I am going to give you 3 minutes. You make your table, plot the 3 functions on this one grid. Good? Okay, so welcome back. Let's start with this first one. The key number is -1. Give me 2 other numbers less than -1. -3 and -7. Love it. Okay. So what is -1 plus 7? -3 plus 7. -7 plus 7. 0. Great. So I'm going to plot those 3 points. -1, 6. Is that going to be an open or closed circle? Yep, correct, because it's equal to 1, 2, 3, 4, 5, 6. Closed circle. -3, 4 is here. And then -7, 0, 4, 5, 6, 7. So it's a linear function that looks like that. Anyone confused or have a question? Speak up now. Okay. I am now going to work on this one here, x cubed. I must include -1. I must include 2. Give me 1 or 2 numbers in between. 0. Okay, we'll do 0 and 1. Okay, what's -1 times -1 times -1? Excellent. What's 0 times 0 times 0? What's 1 times 1 times 1? What's 2 times 2 times 2? 8. Beautiful. Let's plot these points. Do I have any closed circles? No. So -1 is here. Open. That's open. It might be hard to see because the grid's so small. 0, 0, 1, 1, and 2, 6, 7, 8. So it looks like, oh, I messed that up because that's supposed to be open. So it looks like that, a little bit of a curve. The start and end is open. Okay, last graph. Let's pick up pretty purple. Here we go. I'm going to use the number 2. Give me two numbers bigger than 2. 4 and 8. You guys like big numbers. All right, for every value of y is equal to x, so every input is the same as my output. 2, 4, 8. It's the identity function. 2, 2. 2, 2 is closed. 4, 4. And 8, 8. Sorry, that was supposed to be an 8, whoever thought that. It wasn't supposed to be a 5. I don't know what I was doing. Okay, so it looks like that. Cool? Feeling good about this? Easy? All right. I would like you to simply do example 2. We are not going to talk about example 3 today or example 4 because that's writing the function. So we will bring up that discussion tomorrow. So if you'll go ahead and do example 2, I'm going to give you 2 minutes because it's only two sub-functions. We'll discuss the answer, and then I will talk to you about classwork/homework. Okay, so here we go. I'm going to use -7. Although I really don't like -7. I am going to use -9 because that's easy. -8. All right. So let's start with -9 because it's the easiest. So -9 divided by 3. -3 times 2. -6 plus 6 is 0. Okay? -8 divided by 3. Oh. All right, so this is -16 over 3 plus 6, which is, if I make this, it's going to be 18 over 3, which is 2/3. It's adding fractions, ladies and gentlemen. You better, because you're supposed to be going on to calculus, you better get better at your fractions there. All right, so -14 over 3 plus 18 over 3 is 4 over 3. Okay, so I'm going to put -9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. -8 and 2/3. -8 and 2/3 will go there. And then -7. Okay, so this should be an open circle right here. Sorry, it's hard to tell, but this right here is an open circle. Okay? Okay? Are we good with that? All right, now let's go to a much easier function. So we have -7. Give me two other numbers. 2 and 4. We cannot use -8 because it must be bigger than -7. So the opposite of -7 is the opposite of 2, the opposite of 4, -4. Or you could have said -1 times -7, -1 times 2, -1 times 4. Let's go ahead and plot these. -7, 7. It is a closed dot. 2, -2, and 4, -4. It looks like this. So you should have two linear functions. Questions, comments, or concerns? Okay, please now, yes. Uh-huh. Yes. So what I did is multiplying by 2/3 is tricky. Multiplying by 2/3 is the same as dividing by 3, then timesing by 2. So -9 divided by 3 is -3 times 2 is -6, plus the 6 gave me 0. Now, here, I couldn't do that simple trick because 8 is not divisible by 3. So I simply did -8 times 2 is -16 over 3. And in order to add a whole of 6, 6 needs to be a fraction. 18 over 3, which gives me the common denominator, is the same as 6 wholes. And so then I added that, and I got 2/3. I added here and got 4/3. Are we good? Fractions are not going away. They show up a lot. Okay? And the old pre-calculus, there was lots of fractions, and there was no calculator allowed. So please make sure, if you don't know how to deal with fractions, you might want to watch some videos or come in for help. Okay? All right, so please locate your workbook. Please locate your workbook. I know for notes you didn't need it. Okay. So, all right. Some of you ended up with a double of a page. So find the box of candy, which we did last. And tell me what's behind the box of candy. Okay. You got this, match the graph, and then there's a piecewise graphing. And then that same worksheet shows up again. Did you get a duplicate worksheet? Can you check? Okay, so the first one right after the candy you can tear out and use that as scrap paper because it's a duplicate. No, it's not. Oh, we'll rip it out. Yep. But how does that help? I mean, it helps you to look at it again, but. All right, are we good?